Just a few words of encouragement for wave properties, page 193, which you want to, this is next, you please do read carefully, page 193 through to page 196, onwards, through to page 198 is what it is, and do everything, basically do the little plus box questions, do the green conical flask thing where you do questions 1 and 2, having read that, and do the summary questions, and you're doing a very good job at photoing it and submitting it into me, so that's great. And a couple of you are good at putting in a little extra comment of something you don't understand. I can type back a response, and we can do it like that to make sure that we understand what we're doing. So a few words about this. Just the first bit you'll be fine with. It really is a question of what is phase difference? Well, it is the phase difference. Before phase difference, let me talk you through this page here, because it's all a bit confusing if you're not sure about it. And basically, first of all, these 5 graphs here, I'll just talk you through it. This thing here, figure 3, I would ignore this. It's just, I can't make really head or tail of it. I think what they're trying to say is that the displacement distance graphs, this is the displacement is the distance from the equilibrium position for a point on the wave, the displacement either up, positive, or down, negative. And what they're saying is that you can draw a displacement distance graph for a transverse wave, this wave here, or a what's the other one? Transverse longitudinal wave. And this is their effort at showing you how the points on a longitudinal wave would move forward and backwards for a crest or a trough, and how you could draw this displacement so this point here has moved forwards of its equilibrium position there, you see, and thusly they've described it as having positive displacement in the forwards direction and drawn it as being up here, but of course it's not in the same position. So I don't like this representation. It's never come up in an exam. I wouldn't bother too much with it. This is rather important here, and you can probably work this out yourself. This talks about this is a moving wave, right? So a traveling wave or a progressive wave, those 3 terms, moving, progressive, and traveling, they mean the same thing here. It just means a wave that is moving here from left to right, let's say. And we see here time naught, a trough comes along, moving from left to right. It's going to be moving this way. This point P has to move down in order to, if you like, accommodate the trough. So it'll move down, and a quarter of a wave, what's the wavelength? It's from here to here, isn't it? Yeah, a trough and a peak there. So after a quarter of a wavelength, it's moved a quarter of a wavelength. That point P will be down here, you see. After a further quarter of a wavelength, the point P will have moved back to the equilibrium position. After a further quarter of a wavelength, look, T naught, 1 T over 4. Capital T is the time period, lowercase t is the time. Here, when t equals here, down the bottom, when the time equals the time period, that is one time period has elapsed. And the wave, you can see, is back where it was to begin with, right? So the first image is the same as the 5th image on page 195. Let me carry on. Well, you get the gist. So this is showing you quarter period cycles until we get back to the original position. Of course, this trough here in this top picture has now moved to where point R is, one wavelength along, you see. So let's look at point Q for the sake of argument. It goes, what is it? A trough is a peak is arriving, so Q will go up. Then an equilibrium position is arriving, so Q will go down to equilibrium position, and then it will progressively move down as this trough arrives, and it will move gradually up again as this equilibrium position arrives. So see how Q will go up, down, and back to its original position in one time period. The wave equation, I'm just changing subject a little bit. The wave equation here is something that you met at GCSE. You shouldn't have a problem with that. Phase difference. So let me talk briefly about this. It's the difference between the displacements of particles along a wave, or the difference between the displacements of particles on different waves, either. This chapter only deals with one wave, not comparing waves, but it doesn't matter, it could be the same. Could be two waves and comparing 2 points on 2 different waves, right? It can be measured in degrees or radians. I have a vague memory that we discussed degrees and radians, but if you don't remember, here's my non-maths teacher way of describing it. So basically, what's the circumference of a circle is 2 pi r, where r is the radius, right? So you multiply 2 pi by the radius to get the circumference. Well, 2 pi is 3.14, 2 pi is 6.28, right? So there are, and a radian is the angle subtended when the segment of the circumference, the length of the circumference is equal to the length of this segment of circumference, arc. Arc, if you do maths, you'll know this, where the arc is the same length as the radius length. So I've tried to draw this here. Look, I've got my pencil and I've gone, the radius is about the wood bit and then this bit here. So I've done it same again, notwithstanding the fact that's a curve, this is a straight. So roughly speaking, that's a radian. How many fit in a circle? Well, I've done a rough drawing. You get 1, 2, 3, 4, 5, 6 point something. Well, 6.28 actually, because this 2 pi, isn't it? Get it? So angles can be measured in degrees or radians. So if 360 degrees is 2 pi, 2 pi radians. What would, here look, stop the video and consider the answers. So stop the video. Stop it. Go on, pause it. All right, if you did that, why am I pausing? There's no need. You paused it. You pause. All right. We'll start playing it again. Oh no. I have to work out how to give you instructions here. What did you get for pi? Did you get 180? That's pi radians, isn't it? 3.14 radians. Pi over 2 surely must be 90 degrees, and pi over 4 must be 45 degrees. Super duper. That's that. In the book, you got this funny old equation which labours the point that you might find obvious. So I'll just run through a couple of examples. So look, this is saying, look, you can find the phase difference between 2 points on a wave by dividing the distance between the 2 points by the wavelength. Both these things have to be in the same unit, of course. Millimeters, centimeters, meters, kilometers, doesn't matter as long as they're the same. Then multiplying it by 360 degrees. So here's an example just to help us out. Let's say the wavelength is 3 centimeters and these 2 points on a wave are 1.5 centimeters apart. Here, I've drawn it for you. The distance, this 1.5, is the distance on the x-axis, right? 1.5. If the wavelength is 3 centimeters, clearly this is half of that. They're going to be 1.5 divided by 3 multiplied by 360 is basically half times 360, 180. They're 180 degrees out of, or phase difference, and we call it 180 degrees out of phase. 2 points at the same point are in phase. 2 points, one at a peak, one at a trough, they're 180 degrees out of phase. A point on a peak and a point on a peak, of course, would be either, you could call it 360 degrees out of phase, or it's a cyclical thing, isn't it? I mean, this wave, but you could say that those 2 points are in phase because they will both be exhibiting the same movement. As the wave progresses left to right, those 2 points will both start moving down, won't they? And then up again. So essentially they're in phase, like this, right? These 2 points are 180 degrees out of phase because they will move in opposite directions. Can you see that? So the equilibrium position is coming along here. This point will move down, whilst this point will start to move up. And they'll do this, watch. They'll go like this, and then back again like this. They'll oscillate in opposite directions, yeah, all the time. They're 180 degrees out of phase. Very briefly, if you're on a swing with a friend, you know, and you're swinging backwards and forwards like this in the park, that's out of phase, and that's in phase if you swing together. Yep, and that's in phase. And then you could do 90 degrees out of phase. That'd be fun. So that'd be this point there. Let's say that point would be 90 degrees out of phase with that point and that point, actually. So this would be moving down. This point here would be moving up, right? So you get a sort of a that one would lag behind the phase motion of the displacement would lag the displacement of that point by 90 degrees. This point would be ahead of that point by 90 degrees. Okay, you can rearrange it. You rearrange this little equation here for distance, and I've said a little example, and then I'll stop this recording. Can you everyone just take a moment to appreciate the dappled sunlight coming through the tree through the window here onto my page. This is how I'm doing. This is not an effect. This is real. This is live and direct. Right. So you can rearrange it. Our wavelength, 3 centimeters, multiplied by the phase difference, which in my example for your enjoyment is 270 degrees. So you get 3 times 270 degrees divided by 360 gives us, do the math, and it's 2.25 centimeters, which is, in other words, 3/4 the wavelength, 3/4 of a wavelength phase difference if they have a distance of, if they're 270 degrees out of phase, 270 degrees phase difference, or that's, isn't it, 3/2 pi, or 3 pi over 2, same thing, between the 2 points, then the distance can be this. Okay, right, look, so here's the work to be done by, what's today? It is Tuesday, so I appreciate we're not getting through this as fast as we would were we in school. Message me if you want to go faster. If you don't want to go faster, don't message me. Let's do this, submit this by Friday, shall we? Okay, if you'll get it to me earlier, I'll set you more work earlier. Like I said, do this plus box, do the questions, do this green conical flask thing. Do these summary questions, submit it to me. I've put 2 links on with this homework. Well, 3 links. One is this video. The other 2 are the Southampton University Wave Basics is really nice for looking at. Just look at the first page is the essential thing, but you could always have a click around the information. It's really nice. Ways to represent waves. And then also I found a virtual oscilloscope online, which is rather natty. Have a play around with that. If you do it on a laptop with a microphone, if you whistle, if you put the line mic on the application, and then if you whistle various tones, it'll give you something fairly close to a sine wave, and that might be quite fun. Okay, all right. Stay well. Bye.